Hello friends, welcome to EC Academy.
In this lecture, let us understand the important noise probability density functions, which are also known as noise models. The principal source of noise in digital images arise during image acquisition and or during transmission. So, the noise in an image will arise during image acquisition and during transmission, or only during image acquisition or only during image transmission. During image acquisition, the performance of the image sensor is affected by variety of factors such as environmental conditions. During image transmission, due to interference in the channel used for transmission, the noise will be added into the image. The spatial properties of noise refers to the spatial characteristics of the noise, and the frequency properties of noise refers to the frequency content of noise in Fourier transform. Here, probability density function, which is commonly known as PDF, defines the distribution of noise in an image. It defines the probability of distribution of noise in an image. In this topic, we will discuss most common PDF found in image processing applications. Under that, first one is Gaussian noise, which is also known as normal noise model. The PDF of Gaussian noise can be given as P of z is equal to 1 divided by square root of 2 pi into sigma into e to the power of minus of z minus mu whole square divided by 2 sigma square. In this equation, z represents the gray level of an image, mu represents the mean of average value of z, sigma represents standard deviation, and sigma square represents the variance. The plot of this function is shown here, where in x axis it is the gray level value of an image and in y axis it is the probability density function P of z. The value corresponds to mu minus sigma, and mu plus sigma is 0.607 divided by square root of 2 pi into sigma, and the value which is correspond to mu is 1 divided by square root of 2 pi into sigma. The 70% of values will be in the range of mu minus sigma and mu plus sigma. So, we will be having 70% of values here between these two values, and we will be having 95% of values between mu minus 2 sigma and mu plus 2 sigma. Somewhere here we will be having mu minus 2 sigma, and here it will be mu plus 2 sigma. So, between these two values we will be having almost 95% of values. The Gaussian noise model is most commonly used noise model, because the other noise models can also be approximated as Gaussian noise, and mathematically the Gaussian noise model is easy to calculate. So, that is why Gaussian noise model is most commonly used. The next model is Rayleigh noise model. The PDF of Rayleigh noise model can be given as P of z is equal to 2 by b into z minus a into e to the power of minus of z minus a square divided by b. Here a and b are non-negative integer. This equation will be for z value greater than or equal to a. So, z value greater than or equal to a. So, you will get this equation. If z value is less than a, the PDF will be 0. The mean value can be given as mu is equal to a plus square root of pi b divided by 4, and variance is sigma square is equal to b into 4 plus pi divided by 4. So, this is the plot of this equation for Rayleigh noise model. Next model is Erlang or gamma noise model. The PDF can be given as P of z is equal to a to the power of b z to the power of b minus 1 divided by b minus 1 factorial into exponential to the power of minus a z for z value greater than or equal to 0, and if z value is less than 0, this PDF will be 0. Mean can be given as mu is equal to b by a, and variance is sigma square is equal to b by a square. So, this is the plot of this equation. Here the value of k will be equal to a into b minus 1 whole to the power of b minus 1 divided by b minus 1 factorial into exponential to the power of minus of b minus 1. This Erlang noise model is also known as gamma noise model only when the denominator term is gamma function, gamma of b. So, if the denominator function is gamma of b, then this model will act as gamma noise model. Next is exponential noise model. The probability density function can be given as p of z is equal to a into e to the power of minus a z for z value greater than or equal to 0, and it will be 0 for z value less than 0. So, this is the plot of this equation, and you can see it is exponentially decaying function because exponential term is negative here. The mean can be given as mu is equal to 1 by a, and variance is sigma square is equal to 1 divided by a square. This exponential noise model is a special case of Erlang noise model. If we make b is equal to 0 in this equation, you will get this plot. Next model is uniform noise model. The PDF is given as p of z is equal to 1 by b minus a for the gray level value ranging between a to b. For other values of gray level, the PDF will be 0. So, you can see z value ranging between a to b, the value is 1 divided by b minus a. For other values, it is 0. The mean is given as a plus b divided by 2, and the variance is given as b plus a whole square divided by 12. Here, the Gaussian noise arise in an image due to the factors such as electronic circuit noise and sensor noise due to poor illumination or high temperature. Rayleigh noise density is helpful in range imaging. Range imaging is used in digital cameras. The exponential and gamma densities find the applications in laser imaging, and uniform density is useful as the basis of numerous random number generations that are used in simulations. The next type of noise model is salt and pepper noise model, which is also known as impulse noise. The PDF can be given as p of z is equal to PA for z is equal to A, and p of z will be equal to PB for z is equal to B. For other values, the PDF will be 0. Here, if B is greater than A, the gray level B will appear as light dot in an image, and gray level A appear as dark dot in an image. If either PA or PB is equal to 0, then the impulse noise is known as unipolar because it will be having only one probability. If PA is approximately equal to PB, the impulse noise values will resemble the salt and pepper granules, which are randomly distributed over the image. So, this is the reason the bipolar impulse noise is also known as salt and pepper noise, which is also known as short and spike noise. These noise impulses can be negative or positive. For the negative value of impulses, the A and B value will be saturated. As a result, the negative impulses appear as black points which look like pepper, and positive impulses will appear as white point which look like salt. So, that is why we call this as salt and pepper noise. For an 8-bit image, A value will be equal to 0, that appear as black, and B value will be equal to 255, that will appear as white. The impulse noise or salt and pepper noise will appear when faulty switching takes place during the imaging. So, this is about the different noise models or important noise probability density functions. Hope you have understood the topic. Thank you.